Okay, so uh, last time, so we discussed that, well, the relation between the domain of any harmonic functions and having its own complex conjugate. And it turns out that if your harmonic function has a domain and which is simply connected, then that harmonic function always allows its own complex conjugate. So in other words, so therefore, you can consider the harmonic function as a real part of some complex analytic function. Okay. And today we're going to do a little bit preliminaries on the applications of complex analysis. So more explicitly, so we want to do something like solving the Laplace equations on some domain, and in particular, when you have very specific boundary conditions. So solving a Laplace equation under the condition, well, subject to some boundary condition is, we say, a Dirichlet problem. And so, today we will be solving the Dirichlet problem. And in order to do that, I will need to do just one more preliminaries for that. And the theorem goes like this. I have, suppose that I have a function h I have a function. This is domain of your function, my function h, and this is not a complex values function, but this is a real values function. And we are assuming that this is a harmonic function. Then I say that if I have an analytic function, so u x y plus I times v x y, and if I have an analytic function, then the composition of these two and v x y is harmonic. So in picture, looks like this. I have a W plane which has the U and V coordinate. And this is the V plane with X and Y coordinate. And this is some domain. This is domain, which is dW. And on this domain, I have a harmonic function from this domain to real numbers. And the theorem says if I have some analytic function from here to there, then composition of these two. Then this composition function must have the domain on this V plane. And the theorem says that this is still analytic. Okay. So how do I know that? Okay. So when I was trying to prove this, there are two strategies came to my mind. The first one is, you know the definition of the harmonic function. So therefore, you try to differentiate this guy twice with respect to x and with respect to y twice. Then you add them together, and maybe by some little help from the Cauchy-Riemann equations and chain rules from the multivariable calculus. And I'm pretty sure that turns out to be good. This is my plan one. Okay, which is very straightforward, but not very exciting. But the another method is a little bit more exciting, I think. So what is that? So suppose that this domain dW is simply connected. So if this guy is simply connected, then this function is a harmonic on the simply connected domain. Therefore, this guy must allow some its own complex conjugate, right? So h plus I times, well, maybe g. I say this is phi. And so therefore, since this guy has its own complex conjugate, therefore this function must be analytic function on this domain. And you know what? Composition of two analytic functions is still analytic on this domain, right? And the real part of this is clearly u is u, x, y, and v. Okay. And it's easy, and it is easy to see that real part of this composition function is precisely the function that it shows. And well, therefore, any real or imaginary part of analytic function must be automatically harmonic. Therefore, this function must be harmonic, right? Okay, great. Oh, by the way, what if my domain dw is not simply connected? Well, in this case, but this is still doable because suppose that this guy is not simply connected. Or maybe so. So if dw is not simply connected, but well, there's nothing to worry about because being harmonic is actually a local condition, not a global condition. Therefore, even if your function is not simply connected, so even if your domain is not simply connected, but well, you can always find a point v, 0, which is mapped to this point, and on this point, you can always find a small neighborhood centered at this point, and which is still simply connected. Yeah, even though this entire domain is not simply connected, but this tiny little neighborhood of around this point must be simply connected, right? Therefore, this guy, my function h on this domain must be still analytic. Therefore, the composition of this function at this point must be still harmonic, right? And you can, by applying the same argument for each of these points on your domain V, then I guess you can easily show that your composition function is still harmonic. So this is basically the idea. Okay, all right. Maybe I am feeling lazy, so maybe I was too lazy to write down the entire proof, the formal proof of this, but I hope you get the idea. Okay. All right. So as an exercise. Okay, now we are done. Now we are finally ready to go to the applicator solving the Dirichlet problems. Okay. Suppose that I have a two-variable function f. This is a C1 function. So and this P is a point in R2. Now I want to define the notion of the directional derivative is a two-dimensional vector. Oh, sorry. Two dimensions. So I should emphasize that this is a unit vector. Unit vector. Then the directional derivative the derivative of f in the direction of v at p is written as p plus t times v, and this. This is the direct directional derivative. So, okay, so what does it mean? So, well, I guess most of you, many of you, maybe have forgotten the definition of the multiple, that definition of the direct directional derivative. So I think this is the right time to give you a quick reminder. Well, it goes like this. I have a function defined on some open set in R2, and this is P, and P plus T times V is, this is what? This is actually nothing but the parameterization of a line segment passing through P when P t equals to 0, like this, okay? So this is the parameterization of this curve, the parameterization of this straight line. So therefore, under this parameterization, so this T, this guy is now being mapped to this curve. And well, from this definition, I am composing this curve with this real valued function, right? So composing this guy with this, so this fp plus tv is actually nothing but a single variable function, which is what? A single variable function whose independent variable is just t alone. And what I'm going to do is I am taking the derivative of this guy with respect to t, and I plug in t equals to 0. So I am interested, in other words, I am interested in finding the derivative of this composition function when t equals to 0, right? So this is our notion of the directional derivative. Okay. And I hope you remember this, but it turns out this is the same as the gradient of vector field, the gradient vector of f at p with taken inner product with this unit vector v. So in other words, this is the partial derivative of f with respect to x and partial derivative with respect to y. So taken inner product with. Okay. So this is the directional derivative. Okay. Now what? Now I want to consider f is now I have a curve. This is smooth curve in R2, and if n is a unit normal vector field, on this curve C, then for each point P on C, we define is so this is okay. So I think this also requires a little bit of explanation. So I have plane and I have a curve phi, and well, suppose that I have some unit normal vector field. Well, it has two directions, but it doesn't matter which one you choose. But so suppose that I choose just any, so either one of these two unit normal vector field along phi. Then, well, on this domain, I have a function f from defined on this entire domain to the real numbers, and this df over dn at p means nothing but the directional derivative on this direction. Not a big deal. Okay, great. And also, I want to point out this. So I told you that we are interested in solving the Laplace equation on some certain domain with little help from some boundary conditions. What? Okay, all right. Then this Laplace equation is, well, by own its nature, that is very much related to the heat equation. Well, by the way, what is the heat equation? Do you remember this? The heat, well, the heat equation is this is what we call it the heat equation. Okay, so well, more precisely, so well, usually u is a 4-variable function. So well, 3 spatial variables with 1 time variable, right? So uxx plus uyy plus ugg is some diffusion constant. Well, this is usually some positive number. Well, so this is the heat equation. So what does it say? So it says, well, if your Laplacian, so if your Laplacian is positive, in other words, Laplacian being positive means your function value of this guy is, well, relatively higher than the function value. Sorry, if Laplacian positive means that the function value of this guy, if the function value of this guy is relatively smaller than its own neighbor. In this case, it's if Laplacian is positive, so if your temperature is less than your neighborhood, then the rate of change of your temperature is positive, right? So your temperature must go up. On the other hand, if Laplacian is negative, if you are, in other words, if your temperature compared to your neighborhood is higher than your neighborhood, then this guy should be negative. So therefore, your temperature must be go down. So this is the nature of the heat equation. But we are not interested in this general heat equation, but we are interested in the steady state of the heat equation. So what do I mean by steady state? So being steady state means the temperature doesn't change at all, because if the sufficiently enough time passed, then well, temperature no longer change. The temperature no longer changes. So temperature is just remain in steady state. So if there is no external heat source or whatsoever, then well, then everything will be just equals to 0. But well, you know, in some cases there must be some constant. Well, for some boundary conditions, suppose that well, one side of your room is facing a constant temperature equals to 1. Well, in that case, your steady state must be somehow different from the 0. But I mean, the steady state means there is no temperature change. Therefore, steady state solution is very much related to the harmonic functions. Okay, so today we are going to talk about the heat and temperature. And the most important law that governs the entire chapter is the Fourier's law. So it goes like this. I have a function. So this is a real number. And this means the temperature at point xy. Oh, sorry, just one more thing. Well, usually it is very natural to consider the heat equation in 3 dimensions. Why? Because we are living in the 3 dimensions. However, since I'm trying to make a connection between the temperature and the complex analysis. So therefore, all I can do is just a 2-dimensional heat equation. Okay, so please understand. So we are interested in the 2-dimensional heat equation. T is a 2-variable, just a 2-variable function. Okay. All right, and I have a curve. A curve in the domain D, and N is a unit normal vector field on C. Then I want to define the flux is defined like this. Minus K times dt dN at P, where P is a point C. Okay, good. Okay, so again, I want to explain this. I have a curve C that looks like this, and this is my choice of the unit vector field on C. And what does it say? What does it say? The flux. So first, I want to explain. I want to explain this flux. So what is the flux? Flux is the amount of energy or amount of calorie which is passing through this curve and per unit time per unit length. And the Fourier's law says that this flux is actually proportional to the directional derivative. So what does it say? So, well, based on the neighborhood of this curve, if the temperature difference across this curve is greater, then well, you're going to lose a lot more heat. Okay, but if the temperature difference is not that great, then that means your directional derivative in the direction of n is also smaller. Therefore, you're gonna lose a less heat than before. And this K. This K is a constant that usually depending on the conductivity. So we usually say this is conduction constant, and K is usually assumed to be positive. So if the temperature difference is great, so suppose that if this side is hotter, and if this side colder, then in this case the directional if temperature of this side is greater than the temperature of this side, therefore the gradient vector must be facing in this direction, I guess. Okay, so therefore in this case the gradient is facing this direction, therefore this number must be somehow negative, but combined with this negative sign, yeah. Good. So this is the amount of energy lost per unit time per unit length. Okay, and K is usually positive. Okay, good. Now I want to derive the harmonic function from this law. So how? Let us consider, well, this tiny rectangle. This side is, well, the coordinate of this guy is, let me say, this is x comma y, and this length is delta x, and this guy is say delta y. And well, and for simplicity, we will be assuming that delta x and delta y, they are very small numbers. Now, well, along this curve, I want to consider, well, we'll be choosing, this is our unit normal vector field along this curve. And I want to consider the amount of the flux, the total flux across this rectangular curve. Okay, so on this side, okay, so I will need to compute 4 different fluxes because this is the union of 4 line segments. Yeah. So what is the flux on this side? So, well, in this case, the unit normal vector field has no y component, it only has the x component. Therefore, and this is just simply gradient. So on this curve, the flux is going to be minus k times Tx, and there is no Ty because this guy only has the x component, and x plus and well, this is not exact number. Well, roughly speaking, so the flux at this flux on this face must be something like no. Oh, sorry, I forgot to multiply by the length of this line segment. So therefore, per unit time, this is the amount of heat that you're losing on this face. Okay, I'm gonna do the exactly same thing for three other faces. On this side, I have like minus k times, and this time around, so I should be Ty and x and y plus delta y multiplied by the length of this line segment is delta x. And for this side, it's going to be minus k Tx x comma y times delta y. Hold on. Oh, sorry. I should get rid of this minus sign because why? Because this vector is just simply minus 1 comma 0. So combined with this. And for the last side, so it's going to be k times Ty x comma y and delta x. Okay, so all right. So taking the sum of all these 4 numbers gonna give you the amount of heat loss per unit time across this curve. But you have to we are actually assuming one very important hypothesis. That is, our hypothesis is there must be no internal heat sink or heat source contained inside of this curve. So therefore, that means some of these 4 numbers must be 0. So this times this plus this plus okay. Now comparing this and this. So well, I feel like maybe I can use the mean value theorem. And this is more or less like minus k times t x x x comma y, and dy carries over times dx, and plus, and for these two guys, well, I can apply the mean value theorem for the y coordinate. So x, y, delta x and delta y, and equals to 0. Okay, so it turns out for every point x comma y, the steady state solution must be harmonic. So this is our first conclusion. Okay. All right. So for the rest of today's lecture, we'll be considering many different examples of differential problems by changing the boundary condition. And our first example is steady temperatures in half plane. The steady state temperatures in a upper half plane. So we will consider the following problem. This is x coordinate and this is y. So this is the upper. We'll be discussing mainly the upper half plane. And I have very interesting condition. So that is this is the point when this is -1 and this is +1. And we are assuming this boundary condition. The temperature on this line segment is said to be constantly equals to 1. Okay, so on this, and for the other side, and temperature at this side is also constantly equals to 0, and it constantly equals to 0. Okay, so this is our boundary condition. Now, my question is, if this is my boundary condition, then what do you think is the steady state temperature on this upper half plane? So we are interested in finding the temperature, the steady state temperature distribution on this upper half plane. Well, we're going to assume some very technical hypothesis, because first we are assuming that this T must be bounded. Well, so we assume that first T is bounded because, well, the temperature goes to infinity. Well, it's not very realistic. Also, as y goes to 0, as y goes to infinity, this temperature distribution will also tends to 0, right? So this is also another, well, realistic assumption. And finally, okay, so these are our two conditions. Okay, all right, so how do I find the solution given this boundary condition? Well, actually, you can actually do this without any knowledge from the complex analysis. Well, that is, so if you have attended partial differential equations course, then, well, you know how to solve this. How? By using the separation of variable technique. And initially you get a solution, and by using the separation of variable technique, and you multiply, and you take advantage of this boundary condition, and probably you need a little help from the Fourier analysis, then you get the number. But that takes a lot of time and effort. And today, I'm going to show you a complete different solution of this Dirichlet problem. We're going to consider a function that looks like I'm going to say this is f of z, whose real part is u and imaginary part is v. Okay. Right. So since we are using the natural log function, so probably it's better for me to define, well, choose a very specific branch of this function. So in order to choose the branch, so let us consider this. This is point -1 and this is point 1. And so since the natural log was composed with z minus 1 and z plus 1, so simply put, we define z minus 1 equals to r1 minus e to the I theta 1, and z plus 1 is r2 times e to the I theta 2. So in this picture, what is this? So this is going to be R2, and this is R1, right? And well, therefore, I believe it's very natural to say this is my theta 1, this is my theta 2. Okay, so therefore, in this case, then W is natural log of R1 minus R1 over R2 plus I times theta 1 minus theta 2. Okay, so in my picture, this is my theta 1 and this is theta 2. Therefore, I think this angle is going to be theta 1 minus theta 2. Okay. Okay, and since this point is a point on this upper half plane, therefore my theta 1 minus theta 2, I would require that this theta 1 minus theta 2 must be some value between 0 to pi. So, so therefore our branches R1 minus R2 is positive, and theta 1, so I want this guy to be somewhere between 0 to, so minus from here to 2/3 pi, so whatever. So this is my choice of branch. Okay, great. Okay, now what I want to do is, so I want to analyze the image of this upper half plane under this function f. Okay, all right. Okay, so I wanna consider the image of this green line segment, green boundary from -1 to +1. So on this green boundary, this green boundary. So well, if my point is on this green boundary, then I'm pretty sure that in this case, theta 1 minus theta 2 equals to pi, right? So this entire green boundary will be mapped to somewhere around this point. So this is where y. So this is x and this is y. This is u and v. Yeah, and well, so this seems well, and are the ratio between R1 and R2 maybe from positive from well from maybe from let's say from 0 to infinity. Well, so depending on the position of z on this line segment. So this one can, so therefore this one can be anything. So therefore, so x coordinate, u coordinate, the image of the u, so for this image, u coordinate can be any number, and but v coordinate is going to be strictly pi. So this is the, just therefore this is the image of this green segment. Okay, on the other hand, what about this line segment? Well, if my point, this point is on this yellow line segment, and in this case, the theta 1 minus theta 2 should be 0, right? And in this case, the, well, when your point z is on this line segment, then, well, R2 is always greater than R1. So R2 is greater than R1, therefore, oh, sorry, I should be changing the colors, sorry. Sorry, yeah, I'm gonna make it pink. And this guy will be mapping to somewhere around here on this line segment. And finally, this yellow line segment should be like this, I think. Okay. So, so therefore, this entire upper half plane is now being mapped to, sorry, this infinite semi-strip from minus infinity to plus infinity with all pi. Okay, all right. Just one more thing. Since we are looking for the solution whose boundary condition equals to, well, t equals 1 and t is 0 and over here and there, therefore, for our new domain, we should be looking for the solution solution satisfying. And so the temperature at this point is well, identically 1, and temperature on this u axis should be identically 0. Well, if I can find a harmonic function satisfying these conditions, then composition of that solution with this function f, we're also going to give a solution that satisfies these boundary condition on this upper half plane. Okay, all right. Okay, so question is, what do you think is the, can you guess the solution? That is, can you guess any harmonic function satisfying boundary? Well, for me, this is almost very obvious. I feel like I want to choose my function to be okay, because when v equals to 0, implies the u axis. When v equals to 0, the function value equals to 0. But when v equals to pi, then function value equals to 1. And I am pretty sure that this is a harmonic function. Okay, great. So this is much easier to handle. So our guess is t is 1 over pi times b. And well, so technically you should verify that this is indeed a harmonic function. But I believe this is a harmonic function, 100%. U plus t v b equals to 0. Okay. So since I was able to find the solution on this infinite strip, therefore, composing this guy with this, we're going to give us a solution on this plane. So if f is u plus I times v, then composition of my function with this function f is 1 over pi times v. Okay. Well, sorry, but well, maybe I should be abusing argument. Yeah, so I will still call this guy to be my t. If t is a solution at this point. Yeah, sorry, but you know what I mean. Okay, so hey, then what is my v then? Well, previously, my function f was ln of z minus 1 over z plus 1 plus I times the argument of z minus 1 and z plus 1. So in this case, well, since this is the real part, so this is u, and this guy is the v. So therefore, our v is just nothing but the argument of z minus 1 and z plus 1. And well, and I will simplify this, multiplying the complex conjugate of denominator to top and bottom. So z plus 1, z bar plus 1, and z minus 1 times z bar plus 1. And this is, well, since the original question problem was given in x and y coordinates, so I should be better writing, converting everything in terms of x and y coordinates. So therefore, this is x squared plus y squared and z plus z bar, which is 2 times x and plus 1. So this is for denominator. And for the numerator, x squared plus y squared. And z bar minus z bar. So plus I times 2y and minus 1. Okay, so sorry. I changed my mind. So I want this, okay, plus I times 2y. So what is this? So basically, this final expression is, well, you are required to find the argument of a point whose x coordinate is x squared plus y squared. Sorry, x plus 1 squared plus y squared and x squared plus y squared minus 1. And you are supposed to find the argument of this point, 2y. Right? So what is the argument? In this case, I guess this is, well, this is the x coordinate and this is y coordinate. And therefore, an argument is, well, sorry. If this is the point whose coordinate x and y, then argument of this guy is usually taken by taking the arctangent function on y or x. So this is what you are usually supposed to do when you're the freshman calculus, right? So by applying the same trick, this number is going to be the arctangent of this number over this. Okay, so two y over x squared plus y squared minus 1. This one is supposed to be this. There's one more thing to because so previously, so okay, let me go back to my picture. And this argument was supposedly the data 1 minus data 2. And in this picture, so we actually implicitly require that this number is always somewhere between 0 to pi, right? So, and usually when you say about the arctangent function, the range of your arctangent function is usually assumed to be minus pi over 2 from plus pi over 2, right? But in this case, my arctangent function has some slightly unconventional range from 0 to pi. So, therefore, it's going to be like this is pi. This is pi over 2. So the arctangent function that we are looking for in our context, this is the graph of the arctangent function here. So, okay, so I want to point out this. I want to emphasize this. Where this guy. So this is somewhere between from 0 to. Okay, and so the answer is t is, well, hold on, what is my t? My t was just 1 over pi times v, so it's 1 over pi times this guy. Is this really the solution that we are looking for? I'm not pretty sure. Okay, let me try to verify. What if my y equals to 0? So if my y equals to 0, well, then if this is the solution that we are looking for, then if y equals to 0, then the function value must be either 0 or 1, depending on the position of x, right? But if x equals to 0, then it's going to be, what is arctangent of? But if you plug in y equals to 0, then everything is going to be 0. Am I missing anything? Right. Yeah. I will need to make sure that this function must be continuous, right? So suppose that, well, x and y, they are really small numbers, less than 1. Then this denominator must be some negative, right? So denominator must be negative, but a number which is very close to 0, but so denominator is a number which is very close to minus 1, and the numerator is a number which is very close to 0, but still positive, right? So somewhere around here, right? So therefore, in this case, so on this interval, then my function value must be very close to, not 0, but very close to pi, right? So therefore, this is pi, and well, multiplied by this 1 over pi, so the function value is very close to 1. On the other hand, what if if y is very close to 0, but if x is greater than 1, then what do you have? Then y is very close to 0. Therefore, the numerator is number very close to 0, but still positive. And for the denominator, which is still positive, because we are assuming x is greater than 0. So therefore, in this case, we will be choosing a number around here, which is very close to 0. So therefore, the function value here and there must be 0. Okay, right. So this is a right solution. Isn't it great? So we were able to solve this seemingly very complicated Dirichlet problem without any knowledge from the Fourier analysis. Yeah, I really like it. Okay, good. Now I want to consider the next question, next problem. So it goes like this. So this is an x and y coordinate. I have here and there, and minus pi over 2 plus pi over 2. I am interested in finding the solution, the steady state temperature on this semi-infinite strip. So this is D from the x is from minus pi over 2 to plus pi over 2. And y is from 0 to infinity. And I have some boundary conditions. The boundary condition on this and that side, and we are assuming that temperature is set to be 0, equal to 0 constantly. And on this side, we will be assuming that the temperature on this side is set to be constantly 1. So under this boundary condition, I want to find the steady state temperature distribution on this semi-infinite. Okay, yeah, this one is also very challenging, but we have very interesting solution for this. The solution is we consider the following an analytic function. Sine of z, which is sine x cos y. And we already know that, well, the real and imaginary part of the complex sine function. So, okay, so this is the complex sine function. And I am interested in the image of this guy under these complex analytic functions. And what do you think? So this is minus pi, and this is plus pi, and it's plus pi over 2. Minus pi over 2 plus pi over 2. Okay. So this is the u and v coordinate, x and y. Okay. So what about this side? The t is between minus pi over 2 to plus pi over 2. So since this is a part of the x-axis, so well, we will be setting that u is sine x. Sorry, yeah. In order my brain to work, yeah, I will need to write down this too. The coordinate by coordinate, sine hyperbolic of y. And so since this is a part of the x-axis, I will need to say y equals to 0. If y equals to 0, then the v coordinate vanishes. So therefore, and hyperbolic cos is going to be 1. So therefore, my u coordinate is always somewhere between since x is from minus pi to plus pi. So u must be somewhere between minus 1 to plus 1. Okay. So this is minus 1 to plus 1. So now I see. This guy is being mapped to this line segment. What about the others? For this side, this is the case when x equals to minus pi over 2. If x is minus pi over 2, then, well, cosine minus pi over 2 equals to 0. So v coordinate also vanishes. And sine minus pi over 2 is going to be minus 1. So this is constantly minus 1. So therefore, u coordinate is depending solely on hyperbolic cosine. But you know, hyperbolic cosine is always greater than 1, no matter what. So therefore, So this green one, yeah. So this side is being mapped to this one. And finally, I don't want to repeat too much. And you can also easily set this side, it will be mapped to this one. And this interior of your infinite strip will be mapped to this one. Yeah. Great. Hold on. This picture looks very familiar to me. Actually, this is exactly the same picture to the previous exercise. And well, what a coincidence. Well, we actually have the identical boundary condition. So since this blue guy was set to be equals to 1, so the temperature at this side should be 1, 2, and this side and this side is equals to 0. So temperature at this and this guy should be also. And we already know the answer. So in this case, the solution at UV plane is going to be, so what was it? But now, I will need to change U to Y to V. And so U squared and V squared. And this number is, well, 1021. Okay, great. So this is already looking very promising. But well, however, in order to get the complete answer, well, our initial question was given in terms of the x and y coordinate. So I will need to change every u and v in terms of x and y. So therefore, this is, now this is getting a little bit tedious, but I will need to do what I'm supposed to do. So 2 times, what is my v then? Cosine, okay. So this is cosine x and hyperbolic sine of y over u. So sine squared and hyperbolic cosine squared plus cosine squared times hyperbolic sine squared and minus 1. Okay, this is kind of ugly. So allow me to simplify this denominator. So this is, well, sine squared is always 1 minus cosine squared. So this is hyperbolic cosine squared, and this is minus cosine squared cosine hyperbolic cosine, and plus cosine squared and hyperbolic sine squared. So this is minus cosine squared, and hyperbolic cosine squared minus hyperbolic sine squared equals to 1. So this is just 1. And hyperbolic cosine, combining this with this, hyperbolic cosine squared minus 1 is always hyperbolic sine squared. Right. So this is hyperbolic sine squared minus cosine squared. Okay, good. So this is arctangent. There's some tedious exercises. So 2 cosine x hyperbolic sine y and over hyperbolic sine squared minus cosine squared. Well, just a few more tricks. Now what I want to do is I want to divide the top and bottom of this fraction by hyperbolic sine squared. So 2 times cosine x over hyperbolic sine y, and everything by 1 minus cosine x over hyper sine everything squared. Okay, good. Oh, so it turns out this entire function is purely dependent on the ratio between cosine x and hyperbolic sine y. So letting that cosine x over hyperbolic sine y. Okay, hold on. So this guy, this last guy, actually very much like this one looks like this one also looks familiar. So this is well tangent 2 times some angle. It's going to be this. So well, defining that these two ratio equals to tangent of some angle, I would say alpha, then 1 minus this arctangent is tangent 2 times alpha, I guess. Then this is what? This is 1 minus pi, then 2 times alpha. And we require that, and we know that, well, this number, this entire arctangent thing, well, except for this fraction, this entire arctangent function was always assumed to be somewhere between 0 to pi, right? So therefore, I guess this is 2 times pi times alpha. But what is my alpha? This is arctangent of cosine x over hypersine y. But this time around, this arctangent guy, since 2 alpha was somewhere between here, so therefore alpha must be somewhere between 0 to pi over 2. Okay. Okay, good. Wow. Finally, we're getting something. Yeah, I know this is completely unnecessary, but I really want to show you the graph of this function. And I really that if this guy is indeed the solution of this Dirichlet problem. So where am I? So let me go to Desmos. And I want to go to 3D. And Z, it was, what was it? So 2 times pi, and well, arctangent of cosine of x by hypersine of y, and done. Okay. Oh, good. Yeah, this is what exactly we intended, right? So yeah. So this part of this picture graph is the solution. So can you see this? Well, the function value at this point, well, identically equal to 0. And on the other hand, well, if I look at this direction, then the function value from minus pi over 2 to plus pi over 2 is identically 1, and it tends to 0 very beautifully as y goes to infinity. Isn't that great? Yeah, I really like the picture. Okay, all right. Okay, so so far we have discussed very interesting Dirichlet problem, especially when the temperature of the boundary is set to be some constant. So which is also very interesting example. But we are also interested in another very interesting kind of steady state heat problem. So that is sometimes, so even if you do not know the temperature of some side of your domain, but sometimes you want your side, one of your side to be completely insulated. So what do I mean by completely insulated? So that means, do you remember according to Fourier's law, this number actually represents something to do with the heat loss on that side. And if this guy is equals to 0 for entire time, then this condition actually implies that side of your domain is completely insulated. So no heat can flow out or go in. So when a part of boundary is insulated, so yeah, I'm gonna draw a little silly cartoon. So this is a curve, and suppose that this side is completely insulated, this side is insulated, then on this part, we are assuming that dt and dn equals to 0. So this is our condition of being insulated. So there is one very important theorem, and yeah, I don't have much time, but yeah, I hope I can explain this in time. So let us assume this. Let I have a function. This is function from dz to dw, and this is, well, analytic, 1-to-1. And C is a curve in dz, and this large gamma. This is defined to be a image of this curve under function f of C. And we are also assuming that f is conformal at each point of C. Yeah, so you remember the definition of conformal. Being conformal means your function is analytic plus the derivative is non-zero. Then the conclusion is, if a function, this is function defined on W plane, satisfies then this composition function, it also satisfies okay. So before I try to prove this, I will explain. So okay, I will explain the importance of the theorem. So what our idea was, well, so we used the complex analysis to solve the very interesting judicial problem, and the main idea was you are supposed to change some tricky looking domain, some easier domain by choosing some very nice, clever choice of analytic function. So therefore, in order to solve this kind of insulated boundary condition problem, so therefore we are also supposed to be changing the domain from one domain to another. And this condition tells us that this is V plane and this is W plane. Suppose that this is a curve C and this is curve gamma. And if your function is insulated across this curve, along this curve, then your theorem says, aha. 대출 받. If this side is insulated, then the corresponding side in the grid on this plane is also isolated. It's also insulated. This is the idea of the theorem. How can I? Yeah, but unfortunately, so I am running out of time. I'll see you there. Okay.